Hi there. This is a summary of our first lesson on circular areas when we kind of covered the basics of a circle. So in class, the first thing that we did was we looked at just a general formula, or I'm sorry, the general diagram of a circle, and we labeled the circumference of the circle, which is the distance around the circle. The diameter is the distance across the circle, and it goes through the center. And then the radius, of course, you probably know, is the distance from the center to the circumference, right? So it's this line that goes from the center to the edge. And it goes without saying, you probably know that the diameter is double the radius. So we can represent the diameter as 2 times r. So then the first thing I wanted to look at in class was, well, how is the circumference related to the diameter? And so that's where this little investigation comes in that I made. So I'll just kind of go through it for you. I made a little thing here in GeoGebra where we can take the circumference and we can straighten it out like that. And so now this is a straight line that's the exact same length of the circumference. And then by flipping this switch, we unlock this other slider, and then we can kind of see that 1 diameter, 2 diameters, 3 diameters, plus just a little bit more than 3 diameters is what we end up with here. And so the question that I asked everyone to consider is, well, what is up with that just a little bit more than 3 diameters? And then, now we can see that if you lay the circumference back down, you can see how it all kind of lays out along the edge of the circle, right? So it's just a little bit more than 3 diameters. The circumference is always equal to just a little bit more than 3 diameters. And so we thought about it for a little while, and then we realized that if you take the circumference and divide it by the diameter, right, you actually get a little bit more than 3. What you get is approximately 3.141592526535897932384, and so on. You get pi, right? This is where the number pi comes from. Pi is literally any circle's circumference divided by its diameter. It's the ratio of the number of diameters to the number of circumferences, right? We can see that it's 3 plus just a little bit more here. And that little bit more is about 0.14 of a diameter. And so then we went through and just did a little algebra. If we multiply both sides by d for diameter, what we end up with is that the circumference of a circle is equal to pi times the diameter. Okay, so that's a really important thing to know, is that the circumference is pi times diameter. But then we also realize that we can replace diameter with 2 times the radius. That's another important thing to note that you can do. I can replace d with 2r. So the circumference is also pi times 2r, or we actually kind of prefer to rearrange this and we say 2 pi r, 2 times pi times the radius. So either of those were ways that we could calculate the circumference of a circle, right? And again, this all comes from the fact that the circumference of the circle is equal to 1, 2, 3, plus a little bit more diameters, always. So then we looked at the area of a circle, and the next thing I had everyone do over here in GeoGebra was try this slider thing out. And if I made it so that if you cut the circle into a bunch of little pizza slices and you rearrange them into a zigzag pattern like this, we get a different shape. And what we end up getting is a parallelogram. And it's easy to find the area of a parallelogram. But the question that we then had to consider is, what parts of the circle translate to these parts of the parallelogram? So the height of the parallelogram, so first of all, the area of a parallelogram is base times height. But now let's think about what parts of the circle translate to those. So if you think about the height of a parallelogram, it's like the distance, it's this dotted line here, or the distance from between two sides. Well, on the circle, that distance here is what we might call the radius. So the height of the parallelogram is the radius of the circle. So over here, I can replace this height with an r for radius. What about the base of this thing, though? And it's a little hard to see, but the base is, it's a bunch of these, the curves along the outside, which we would call the circumference. However, it's the base length is not the entire circumference, right? It's half of it, because the other half is up here. So we could think of the base as 1/2 times the circumference. So I can replace this base with 1/2 times the circumference. So the area of this parallelogram, as it relates to the circle, is 1/2 times the circumference times the radius. But then, of course, I don't like having two different variables or two different unknowns, circumference and radius. But the circumference is 2 times pi times the radius. So what we did was we then substituted this expression, 2 pi r, in place of the letter c. So we got 1/2 times 2 pi r times r for the area of a circle. And then some neat stuff happens. The 2 and the 1/2 cancel, and r times r is r to the second power. And so we end up getting pi times r to the second power, and which you might have heard is pi r squared is the area of a circle. Okay, so those were the big notes that we came up with. The circumference formula, but then more importantly, the area formula, pi times the radius squared. And then we just spent the last couple minutes of class looking at how to find areas, first expressed in terms of pi, and then expressed in a decimal approximation. And so for this first example, the radius of the circle was 7 centimeters. So we expressed the area in terms of pi by doing pi times 7 squared, and 7 squared is 49. And so we could say that the area of this thing is 49 pi square centimeters. That's how we would express that area. And then we would just grab a calculator, and to do a decimal approximation, I would just take 49 times 3.14159, times pi, and you get approximately 153.9 square centimeters if we just round it to one decimal place. So you can expressing them in terms of pi is often actually how we want to do it, but you can also do a decimal approximation. And then this other last example that we did, the only difference is to note is that the radius is not 22, the diameter is 22, which makes the radius 22 divided by 2, or 11. So then we could find the area in terms of pi by doing pi times 11 squared, which is 121 pi square feet. Or we could then do the decimal approximation. It comes out to just about 380.1 square feet when you plug this into a calculator. So get those notes down, make sure you understand that, and then come to class ready to really dig into some circles. Are we